Welcome to a module on application attacks. This module will deal with typical threats that are representative of the perils that jeopardize modern applications. First, we'll take a look at three of the most widespread attacks. The first exploits a buffer overflow vulnerability. This type of attack aims to take control over or control the execution of a program run by a user. It exploits a flaw of an application, causing it to react in ways that were not provided for by the developers when entering some types of input. The second class of the most prevailing application attacks is SQL query manipulation, or SQL injection. Most modern applications are in fact data-based. The majority of them store configuration data or working data that is subsequently processed on servers. We're not talking here strictly about databases. The servers don't even have to be separate services. In-process servers, servers that are launched by an application itself, have gained popularity. They are still, however, classed as database servers, and still communications are performed via SQL. The third type is cross-site scripting. This attack has been ranked as the most popular threat for years now. Cross-site scripting relies on inserting a code on a website or in a modified link to a website in hopes that visitors will run the code. This hope is not without grounds since web browsers follow a protocol. According to the protocol, browsers should interpret all the data that a web server sends to them and execute or render them in a correct way. The data can also include code that is not directly stored on a page. We'll start with a buffer overflow. The general idea for this attack is that it should enable attackers to take control over a program. A perfect scenario would include the program executing an attacker's code. The attacker doesn't need to have access to the program's source code. This would be the best solution. Not only to modify the program, but also force it to execute arbitrary operations prepared by attackers. Some questions seem to come up at this point. First, how can you change the operation of a program that is compiled? We're referring here to languages like C and C++, the languages where the code is first compiled to a binary version and only then is it distributed. You can't change the code of such programs directly, but you can control its execution. This is possible because for an operating system, for a PC or a processor, program code is not different from data. It's simply strings of zeros and ones loaded into memory somewhere. It's the interpretation of the zeros and ones that matters. A buffer overflow attack might take the following form. We have a compiled program, for example, an exe file, and want to run it. The program has to be loaded into memory. An operating system allocates a place on the stack for the program since it has to control the program in some way. The stack will contain the program's function headers and control register values. The registers will include ESP, where the address of a currently executed function will be located, and EIP, which indicates the data buffer of a currently executed function. As we'll see in a moment, apart from the program data, a stack includes also data pertaining to program execution. It also contains the values of local variables and function call arguments. This is crucial. Note that program structures and user data structures meet in one buffer area. User data is the input stored into a program. Let's take a look at a graphical representation of this. We have a sample function that anticipates a string and will operate on the pointer of that string. The length of the string is specified, which could cause problems. An assumption is that this length will be 128 bytes. What will happen though if the data exceeds this size? We've prepared 128 bytes of space in the stack. What's going to happen if a user will submit a longer string than assumed? The data will overflow the buffer and consequently overwrite the other stack areas. A stack is a FIFO structure. What's important in the image above is that a given area has been allocated, and the data located there is too much. The data needs to be placed somewhere. It overrides adjacent areas that are behind them in the stack. The areas were reserved for other data, for example, for functions that control execution. If a program's execution reaches the point pictured above, which means that the function completes and will try to return control to the original program, it will have to know the address of the function that called it. An assumption is that this address is in the location pictured. This is not true as it turns out. The area is now overwritten with other data. The type of data depends on the length of the input string and the data that was contained in the input. As a consequence, once a function ceases to operate, execution controlling for a given program does not return to the call function, but is instead located in some other place. The question is, what place? In the easiest case, the call parameter is not a simple string, but a fragment of code that an attacker wanted to run. The location of the code was specially selected to overwrite control registers. At this point, the program we run executes a malicious code supplied by an attacker. Consider this potential attack scenario. Step 1 to exploit a buffer overflow flaw is to locate insertion points. A program's interface has to be able to receive data from us and return information on handling the data. For example, prompt error messages. Once we've located such insertion points, we start checking if they are vulnerable to buffer overflow attack. We don't do this on a victim's computer, however, since we don't have control over the program and consequently can't monitor live events and reactions to various types of input. This would be both time-consuming and easy to detect, although it would not prove much of a real problem. If the software is typical, for example it's an FTP server, we only need to install on our local PC the same version of the server. Connection will be established through a debugger that will give us access to all required data. Overriding control registers that manage program execution, for example EIP register, is the key stage of this attack. A function's return address is the value that will be overwritten. The so-called opcode, standard operation codes, will be a valuable aid in this. Making use of them, we won't need to check for our location to override an address manually by trial and error. Instead, we'll find a table that specifies that a given DLL holds EIP register addresses at a specific system address. Opcode documentations are publicly available. At any rate, we need to find the end of a stack. How much has been allocated for our program in the stack? The selected program should at all times be held in the same location in main memory. Ideally, the software should always be running on a victim's computer. This is how system services operate, as well as operating system fragments and so on. You can improve your odds by padding a buffer with no operation instructions. In this way, even if you fail to find the exact desired address space, the address that has the beginning of your malicious code, a CPU will go through the instructions one after another until it slides to your executable code. This technique is known as a NOP slide. A NOP slide is a fairly common method used to increase the chance of successfully running buffer overflow attacks. The last step is to insert malicious code. Up to this point, we have successfully controlled or monitored program execution. We know which memory address holds return addresses, and we know the locations of other addresses that we want to overwrite. Once you enter an address in this location, the new address we submitted should hold a fragment of code. We need to add a payload to the attack.